let's go to another situation now with numbers. So we're facing a question whether to purchase or not to purchase a new educational and entertainment gadget. So this gadget has a few uses, and the first question we're facing is actually, how rich am I? So if we're quite rich, so it varies from very rich to not so rich, and if we're quite rich, we're going to be purchasing this gadget no matter what. Where if we're not so rich, we'll have to think further. So at first, we in that case decide not to purchase the gadget. And if we're very rich, as we said, we will purchase the gadget anyway. Now the second question is, how educated am I? Because even if we're not so rich, if we're quite educated, we might have use for this educational gadget and have a very big need for it. Okay, so here it is. This education will vary from little education to much education, and even if we're not so rich and if we're quite educated, we will purchase the gadget. And if we're not so rich and we are also not so educated, we won't have use for this educational gadget, so we won't make the purchase decision. So here you see that there are a number of things to consider, and now we're going to look at a numerical decision tree on how this decision is really taken. Okay, let's look at the same tree in numeric form. So here it is. We have data coming into the root node, and they either purchased the gadget or not. If they were rich, if the richness was above 83, they purchased the gadget, and if the richness was below 83, they did not, and if the education was considered at the next step, so they still kept on considering, and if education was above 30, they still went ahead and purchased that gadget, no matter that their richness was below 83. And if they, furthermore, having richness below 83, if their education level was also below 30, then they did not finally purchase the gadget as well. So this is essentially the decision tree. But let's take a look at the numbers here. So first of all, those numbers which are essentially percentages but are written out as decimal places numbers. So this 0.76 means that out of the whole pack we're sampling, 76%, well, 76% made the purchase of the gadget, and 24 did not. And now, after we make a split at that tree, we can see that those with richness above 83, 87% of those purchased the gadget, and 13% did not. So it's quite a good split because it gives us a very high percentage of those who are purchasing there by the richness already. Okay, but let's go down the other end, and we can see that this who are not rich situation is not that good. It's quite an equal split, so it's 47% purchasing and 53% does not purchase. But it's good. It's a good thing that we made that split on education furthermore, because now if we look at in here, we have 78% purchasing and 22 not purchasing if you're not rich but educated. And on the other hand, if you're not rich and not educated, then we have 25% only purchasing and 75% does not purchase. So we kind of separated them quite well in this respect. Let me clear this out a little and make a further point. So all the data is entering into the root node, and that means that there's 100% of our sample in there. Now the richness is actually when we consider richness above 83 richness, it's 73% of all that data. And then 27% of all that data is richness below 83. And then we have the education split, which further splits this 27% into 12% of the total, which is richness low, education high, and 15% of the data, which is richness low, education low. So that's kind of how to read into this tree all in all. Let us come back to this problem and let me show how similar those two problems are. furthermore, let me show you when to use what classification, and then what demarcations or what problems come up with the decision trees. So first of all, we have essentially very similar problems. The only thing is that rich is the end of this dimension and not rich is the end of this dimension, and educated is over here, and not educated is over here. And now what we did was, first of all, we don't have three types of movies. We only have those who bought the product and not. So let me make all those blue triangles into red circles instead. And now what we need to do is we need to separate those two. So what we did was we initially drew the line between the rich and the not rich and said that the rich buy, and then the line according to education between the not rich and said that the not rich but educated also buy. And we made a few errors along the way, so these are here. Okay, so this is what we did so far. So what we can note is that with decision trees we can make such straight cuts, like a horizontal cut, a vertical cut, and so forth. Let me first show you what not to do with decision trees. Let's say that we want to get rid of this error here. So we don't like it, we want to get rid of it. Then we do a further cut based on education inside richness, and then a further cut inside that last cut based on richness again. So if we have with rich people extremely not educated but extremely rich, then they will buy. And if we have with rich people extremely not educated but a little bit less rich, they will buy. Okay, so this thing. And let me show you how this is on a decision tree of ours. So first of all, we had rich people. Now we derive a new level of separation based on education. And if education is large, or if it's small, that's our deciding factor. And with education that is small, we derive further based on richness. So richness can be large or small. And those who are rich and education is larger comparatively, these will be buying. So this is our area 1. Those who are rich, education is smaller, but they are extremely rich actually, so the richness is still larger, then those people will also buy. This is our area 2. And thirdly, those people who are rich, their education is smaller, but their richness is not that extremely big, they won't buy. That's a minus, and that's our third area. So let me mark those areas here on that next graph. This is our area 1, this is our area 2, and this is our area 3. So that's essentially what decision trees does. But this, of course, is not a good thing. This thing is called basically overlearning. So we're trying to trying to get from our data every bit and piece correctly, whereas we build a very intricate tree, and the other word for it is overfitting. So, but on the other hand, if we get some kind of a new data piece, it most likely won't work on that. So making the tree too complex is a bad thing. So a further point to make is that there are other classification methods. One of them is linear classification. And what this linear classification does, it has the ability of drawing a single line through the data. So it would separate the do's and the don'ts like that. Here, it's actually even better than our decision tree, because it would make a single mistake here, and the rest of it would be correct. But generally, I think decision trees are worth a try, and they're very good with all those things, because you can think of it. there is only one line at your disposal with linear classification, whereas with decision trees you can build many boxes. Not just the only thing is not to overlearn, so to say, or overfit.